Recursive definitions can be very helpful when you look at a small section of a sequence. However, if you want to know both a sub 3, the third term in the sequence, and a sub 5000, the 5000th term of a sequence, an explicit formula often works better. Problem number 3, writing an explicit formula for a sequence. The question asks, what is the 100th term of the pyramid sequence? So let's consider the method that we've already seen. Well, we realize the first term would be 1, the second term is 1 plus 2 or 3, and then we add 3 more to that, we add 4, we add 5, we add 6, we add 7, we add 8. But if we want to know the 100th term and we just followed this pattern, well, we end up just adding plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, and we'd have to keep going until we got to the 100th term because we have a recursive definition of this pattern or this sequence. And I've seen students on their calculators plus 2, plus 3, plus 4, plus 5 in problems like this and continue through possibly as many as 100 iterations. And then, around step 52, they lose track of how many and have to start over. It's a big mess. It works. There is a much simpler way, and that will be the use of an explicit formula or explicit definition of each term in our sequence. And what the explicit formula will give us is a way to substitute in our index value, n, in this case 100, and evaluate a simple algebra expression to find our 100th term in the sequence. Here's how we can set to work finding an explicit formula. First, we should expand the first few terms of the pyramid sequence. So take a look at the table. We see a sub 1. Remember, that will be the first term in our sequence. We know that's 1. There's 1 square in that pyramid. And, well, 1 down below still equals 1. The expression was not as interesting as some of these expressions. We'll soon see. A sub 2, our second term in the sequence, will be a sub 1, which was 1, plus 2 more. That's using our recursive definition. We look back one value and add 2 more. We're moving toward an explicit definition or an explicit formula. So let's continue. 1 plus 2, of course, equals 3. A sub 3 equals 1, which now perhaps we should think of that 1 as being the number of squares in the first row, or the topmost row, plus 2, the second row, plus 3, the third row, and that equals 6. A sub 4, similarly, will equal 1 plus 2 plus 3 plus 4, and that's 10. A sub 5, you can see here, the pattern continues all the way through a sub n. And here's where we take a bit of a stretch from very concrete values to a more arbitrary concept. So some term, some nth term in our sequence, we'll call it a sub n. Remember, that's an index value of n, will equal 1 plus 2 plus, the pattern continues, all the way through n. So if n is 100, we would have 1 plus 2 plus 3 plus 4, skip a few, plus 99 plus 100. Therefore, a sub n equals more or less what I just said, 1 plus 2 plus 3 plus skip a few, because we recognize that pattern, all the way until we get to n minus 2. Notice that will be the value 2 terms before n in the sequence. And then the term n minus 1, that will be the term immediately preceding the term n, and finally the term n. So it will be the sum of all of those, which we can rewrite in this order. It can be n plus n minus 1 plus n minus 2 plus, and the pattern continues until we get to plus 3 plus 2 plus 1. 1, of course, being our first value, or our a sub 1 value, in this sequence. Adding the two previous equations gives us the following result. We saw previously on the last slide, a sub n equals 1 plus 2 plus 3 plus, all the way through plus n. We rewrote that equation, or at least the expression on the right-hand side, by reversing its order. So note the n plus n minus 1 plus n minus 2, all the way down through plus 3 plus 2 plus 1. These are lined up in a very particular order. It's going to accomplish something that's really neat, and a neat example of what algebra can do for you. I just hope that you understand it well enough to appreciate it. It's the kind of thing that you wonder about the first person to attempt to solve a problem this way. How, what an outside-the-box style thinker they were. Well, let's move on, and we'll see how well you understand and how much you appreciate this technique. So, someone thought, let's rewrite the equation or the expression in reverse order, and why not add the two? Maybe they were bored. Let's just add these two equations and see what happens. Maybe they had a motive and a goal in mind. So note the left-hand side of those equal signs, a sub n plus a sub n equals 2a sub n. That equals, well, note 1 plus n is n plus 1. Notice 2 plus n minus 1 equals n plus 1. Notice also 3 plus n minus 2 equals n plus 1. So this is some of that neatness I was talking about. It's amazing how these things add up just right to give us the same repeated binomial being added together. Notice that continues all the way through this middle section that we've kind of eclipsed, we've skipped through, to the far right-hand side. N minus 2 plus 3 is n plus 1. N minus 1 plus 2 is n plus 1. And n plus 1, believe it or not, is n plus 1. Simplifying, we have 2a sub n equals n times n plus 1. Because note, we have n terms being added together, and when we added those two equations, we're going to have n instances of n plus 1s being added together. If we counted these up, well, 1, 2, 3, it went all the way up through n. So therefore, we have n times n plus 1 on the right-hand side of the equation. To solve for a sub n, recall that's our goal, is to write any term in the sequence, a sub n, as, well, some expression that we can solve. So if we check it out, divide both sides of the equation by 2 to find a sub n equals 1/2 times n times the binomial n plus 1. There's our explicit formula. We can find the 100th term relatively quickly and easily without going through 99 iterations of using a recursive formula. Substitute 100 for n. 100 plus 1, that's 101. 1/2 times 100, that's 50. So we end up with 50 times 101, and I just glanced down at the bottom, looks like that's going to be 5,050. Therefore, the 100th term is 5,050. Neat. Algebra, it's a beautiful thing. And a chance to show that you have got it. A. What is an explicit formula for the sequence 0, 3, 8, 15, 24, etc.? And what is the 20th term? B. A reasoning question. Why is using an explicit formula often more efficient than using a recursive definition?